The human gastrointestinal tract is a highly automated machine. From the moment food leaves your stomach, the gut has to continuously balance three competing tasks: digesting nutrients, propelling waste in one direction, and keeping its own lumen clean. To pull this off, the small intestine relies on two distinct mechanical movements. The first is segmentation, which dominates while you're actively digesting a meal. Think of segmentation like hand-washing clothes in a basin. You aren't pushing the clothes forward, you're scrubbing and churning them in place. The gut wall contracts in localized rings, dividing the lumen into segments and chopping the chyme back and forth. This ensures every drop of fluid makes physical contact with your absorptive microvilli. This diagram compares that churning action with the second movement, peristalsis. While segmentation mixes, peristalsis pushes. It's a progressive wave that forces chyme steadily toward the large intestine. To move a passenger tricycle out of a muddy road, you have to stand behind it and push forward, while simultaneously clearing the obstacles out of the way in front. The gut propels food using that exact same physical logic. This flowchart maps out the neurophysiology behind that movement, governed by a strict rule called the law of the intestine. When a bolus of food distends the gut wall, mechanical stretch receptors immediately activate myenteric sensory afferents. Those sensory neurons trigger a perfectly polarized response. Behind the bolus, excitatory interneurons release acetylcholine and substance P, causing the circular muscle to contract and build high pressure. In front of the bolus, inhibitory interneurons release nitric oxide and VIP, relaxing the muscle to create a low-pressure receptive zone. High pressure behind, zero resistance in front. The food has nowhere to go but down. After digestion finishes and you enter a fasting state, segmentation and localized peristalsis stop completely. They are replaced by the migrating motor complex. Driven by peaks of the hormone motilin, this intense, sweeping wave acts as a night cleaning crew, clearing out leftover debris and mucus. The moment you take another bite of food, the complex shuts down instantly. This strict alternation ensures you maximize nutrient extraction when food is present and sweep the tract totally clean when it's empty, preventing bacteria from migrating up from the large intestine. Once the small intestine finishes its work, the large intestine takes over, absorbing water and using specialized high-amplitude mass movements to push feces over long distances. Eventually, this forces the fecal matter into the rectum, initiating the defecation reflex. Looking at this diagram of the defecation cascade, we can see it operates on a dual loop system. The local enteric nervous system senses rectal stretch and initiates a weak intrinsic reflex. But to actually achieve voiding, those local signals have to recruit the heavy machinery. Sensory signals travel via pelvic nerve afferents up to the S2 through S4 segments of the spinal cord. The spinal cord processes this stretch and fires back a massive parasympathetic efferent discharge. These motor fibers travel back down the pelvic nerve, dumping acetylcholine onto M3 receptors to drive powerful rectal contractions. At the same time, this circuit forces the involuntary internal anal sphincter to relax. This table outlines the final boundary of control. While the parasympathetic pelvic nerve opens the internal sphincter, voiding doesn't happen automatically. The external anal sphincter is composed of skeletal muscle and controlled by the somatic pudendal nerve. Your cerebral cortex actively maintains tone in this nerve, keeping the door shut until you consciously decide to release it. We can see how vital these local ganglia are by looking at what happens when they fail to form. In Hirschsprung's disease, an embryological defect prevents neural crest cells from migrating fully into the distal colon and rectum. Because this specific segment lacks enteric ganglia, it completely lacks the inhibitory neurons needed to release nitric oxide and VIP. Without those relaxants, the affected smooth muscle remains permanently locked in a tight tonic contraction. Feces pile up behind the blockage, ballooning the healthy proximal colon outward and causing megacolon. Safe waste elimination relies entirely on a continuous chain of communication: local stretch sensors, spinal parasympathetic reinforcements, and voluntary cortical override. Removing a single cellular link from that chain creates a functional, life-threatening obstruction. The physical movements of the gut are only half the equation. The tract also deploys a vast chemical regulatory network to perfectly match motility and glandular secretions to the specific composition of whatever meal you just ate. This diagram maps the duodenal enteroendocrine network. Sensor cells sample incoming chyme, I cells detect fats, S cells high acid, K cells glucose. Panning down to their responses, K cells release GIP for insulin, S cells release secretin for bicarbonate, and I cells release CCK to contract the gallbladder. Let's test this practically. If a patient consumes a heavy, fat-rich meal, which specific duodenal cell and resulting hormone are responsible for triggering their gallbladder to contract? The fat triggers the I cells, which release CCK. This mucosal mapping also explains the incretin effect. If you drink a glucose solution, your blood insulin will spike significantly higher and faster than if we injected that exact same amount of glucose directly into your veins. The oral glucose physically contacts the K cells in the gut wall, triggering a massive release of GIP into the blood that pre-activates your pancreatic beta cells before the sugar even hits your systemic circulation. When these endocrine loops fail, the downstream effects are severe. In Zollinger-Ellison syndrome, a neuroendocrine tumor called a gastrinoma pumps unregulated massive quantities of the hormone gastrin into the blood. This hyperstimulates the stomach's parietal cells, generating a relentless flood of hydrochloric acid. This immense acid volume overwhelms the neutralizing bicarbonate in the duodenum, plummeting the luminal pH below 2.0. At that extreme acidity, pancreatic lipase is instantly denatured and destroyed. Without functional lipase, dietary fats cannot be digested or absorbed, leaving the patient with profound fat malabsorption and staturia. The gut uses three pillars: motility, neural reflexes, and chemical messengers. For exams, acetylcholine and substance P contract muscle behind food, while nitric oxide and VIP relax it ahead. Also, the pelvic nerve relaxes the internal sphincter, while the pudendal nerve contracts the external. When you secure your understanding of normal physiology, the sensors, the nerves, the muscles, diagnosing complex pathologies becomes a matter of pure, simple logic.